who's going to tell us about Lie algebras.
I'm going to start about... So in some sense, quantum groups are a generalization of Lie algebras. So let me start by telling you... Is the sound okay? Or I fear that this... So let me start with Lie algebras. And I should be a little bit more specific here. By Lie algebra, I mean finite-dimensional simple Lie algebras. The first example is the Lie algebra SL2, which is the set of 2 by 2 matrices whose trace is a 0. And I mean, that's a description of the Lie algebra. The Lie bracket is given by A Lie bracket B is AB minus BA, and you can check that the trace, this condition is preserved. But that's not really the way I want to think about it. What I want to think is I want to think of SL2 as being spanned by 3 elements, H, E, and F. And I want to just give the Lie bracket directly on these generators without referring to them as 2 by 2 matrices. So the Lie bracket is given by those formulas. H bracket E is 2E, H bracket F is minus 2F, and E bracket F is H. And if you like to think of H, E, and F as 2 by 2 matrices, I can tell you what they are. So H is 1, 0, 0, minus 1. E is 0, 1, 0, 0. And F is 0, 0, 1, 0. But this is something I don't care about. I'm going to think of Lie algebras as being given in this particular way. Turns out that it's isomorphic to that. Lie algebras are important, and it's certainly a good goal to try to understand their structure, but representations of Lie algebras are equally important, and understanding the structure of representations is, for me, just as important as understanding the structure of Lie algebras. So, okay, here I gave you a Lie algebra, but I haven't told you what its representations look like. So let me first tell you what representations of SL2 look like. And by representations, I mean finite dimensional representations for the moment. Okay, so here's what a picture of a representation of SL2 looks like. There's one representation for each dimension. And I'm going to do the, let's say, how many dots fit in here? 5 dots fit nicely, so I'm going to do the 5-dimensional representation, and from this picture it's going to be obvious how to generalize. So I'm going to pick some colors, and let's see. I'm going to draw E in red, F in green, and H in purple. Those dots represent basis elements, and this is what E does. E sends this basis element to the next one, and so on, and so on. F does the opposite. And H sends each basis element to itself. So now that's not the complete picture. To have the complete picture, I also need to tell you with what multiplicities these things happen. So this basis element goes to that one, but this one goes to that one times 2, and that's why I put a little 2 here. And this basis element goes to that one times 3, and so on. The F's do the same thing in the other direction. And finally, H, H actually sends this vector to 0. But I'm going to say that it sends it to 0 times itself. And this sends it to 2 times itself, 4 times itself, minus 2, and minus 4 times itself. OK, so here I gave you something, and I'm telling you this is a representation. But there's something to be checked to know that it's indeed a representation. You need to check that those relations are satisfied for these particular actions of h, e, and f. So let's do just one of the verifications, just for fun. So we pick this vector here, and we're going to check that last relation. So that last relation says EF minus FE equals H. Well, what is EF? So first do F, then do E. So I start here, do F, I land in twice this vector, then do E, I land in 6 times that vector. So that's 6. OK, FE, I first do E, I land in 4 times this vector, come back, that's 4. And H, well, that's the number in purple, which is 2. And sure enough, 6 minus 4 is equal to 2. So we're happy. We have checked that one relation at the one particular spot. If you wanted to check everything, you would need to check all 3 relations at all spots. It turns out that it's fairly easy to do it. I'm not going to do it right now. So let me go to another Lie algebra, which is a little bit more complicated. And that's the Lie algebra SL3.
Excuse me.
Yes?
What about the last point? You forgot to tell what happens when you act with H. I'm sorry, with F to the last one.
So F applied to this is this one.
No, I mean H. No, E.
E is 0 on that.
Ah, okay.
So, well, we can check that relation, that EF equals H. So that's like 1 times 4 minus 0 is equal to 4. So it works out. I mean, yeah, OK. It's, when there's no arrow coming out, it means that it goes to 0. So before telling you what SL3 is, I'm going to tell you what its representations look like. And then we're going to work backwards towards the structure of what SL3 is. So there's now 2 generators that deserve to be called E. So I'll call them E1 and E2. E1 is drawn in red, and E2 is drawn in green in that picture. There's E1 and E2. There's also F1 and F2. F1 and F2 follow the same arrows, but in the other direction. And there are some coefficients that I didn't put here. It would be a little bit too cluttered if I put all the coefficients. So there's also F1 and F2 that are not indicated, but so F1 goes this way following the red things, and F2 goes this way following the green things. And finally, there's H1 and H2. So let me tell you what H1 and H2 are. So I'm going to need 2 more colors. So I start with H1 in blue. So it sends everything to itself, but with a given coefficient. So here I draw it like this, but I really mean this vector, this basis vector goes to itself, that one goes to itself, that one goes to itself. And the coefficient is, well, let me just draw it. So this is 0, this is 1, this is 1, this is 1, this is 2, this is 2, this is 2, this is 3, 3, 3, 4, 4, and 5. You sort of look how far you are on the x-axis, and that's how you determine what H1 does. And then there's H2, which does something very similar, except with some other orientation. So H2, again, it acts on each one of these things by sending it to a multiple of itself. So let's see. So now I sort of have to put myself on this axis. So this is 0, and now that's 2, that's 4, that's minus 2, that's minus 4. Yeah, I could keep going. I mean, this one here is, well, how far is it on this axis? So that would be 0, so that's 2. And this one is 3. So, okay. Do you get the idea? So that's what SL3 representations look like. But I haven't told you what SL3 is. Well, okay. You probably maybe know SL3 is the collection of traceless 3x3 matrices. So I could just say that E1 is 0, 1, 0, 0, 0, 0, 0, 0, 0. E2 is 0, 0, 0, 0, 0, 1, 0, 0, 0. H1 is 1, minus 1, 0 on the diagonal. H2 is 0, 1, minus 1 on the diagonal. F1 is the transpose of E1, and F2 is the transpose of E2. So, okay, if that makes you feel comfortable, here it is. But actually, I'm not going to use this description, because that's a description that does not generalize to the case of arbitrary Lie algebras. Well, the Lie algebra SL3 certainly acts on itself. There's this adjoint representation, so I can use the same kind of pictorial notation to say what SL3 is. And so let me draw SL3. So there's 2 points that live at the origin, and then there is a hexagon. And I have E1 is this guy. F1 is there. We have E2 up here. F2. So E1, the action of E1 is pushing to the right. So if I want to also have a name for this guy here, well, that's E1 acting on E2. So I didn't put it as a generator because it can actually be obtained as E1, E2. And the guy that's here in the middle is H1. By the way, the collection H1, E1, F1 forms a subalgebra isomorphic to SL2. Same thing for the collection H2, E2, F2. That also forms a subalgebra isomorphic to SL2. So E2 pushes this way. So that is, and down here we have, of course, F1, F2. And I'm not worrying about coefficients in this particular story. This picture here that just contains the basic shape of that Lie algebra, that is called the root system. And each Lie algebra has a different root system that looks differently. So some other examples of root systems that exist. So these are root systems of other Lie algebras. They're not root systems of SL3. So there's one that looks like this. So draw a square with 9 dots, and then there's this one. There's a Lie algebra that has that shape, and there's also a Lie algebra that has this shape. And by the way, this is called type A2, this is called type B2, and this is called type G2. There's actually many more examples of root systems, but they live in higher dimensions. So they're somehow more difficult to draw. For SL2, the root system for SL2 is just lives in a one-dimensional space and looks like this. So let me use these pictures to introduce some terminology. The set of all things that you get by using e's and bracketing them together, that's called, okay, these little arrows that I draw, these are called the roots. And then the arrows that are on that side of the picture are called the positive roots. So these are the positive roots. In those examples, that would be, let's say, this. And you need to pick a half of the root system, and you call it the positive roots. So, and it's denoted delta plus. So delta plus is the set of positive roots. In this example, delta plus is just E on its own. Of course, one has the notion of negative roots. These are the other ones. I would call it delta minus if I needed to call it anything. I don't think I'll need it. And yep. So fair enough. So I gave you some examples of Lie algebras, some in more details than others. But let me now give you the general story. So the way to build a general finite dimensional simple Lie algebras is as follows. So you start with one of the following so-called Dynkin diagrams. So either 1 point, or 2 points connected, or 3 points connected, or 4 points connected. And these are called type AN. Or 2 points connected by a double connection with an arrow, and then we can have the same thing with an extra simple connection here, like that. So these are called type Bn. The n here is the number of nodes that I have there. Corresponds to the number of EIs. The same as BNs, but with the arrow going in the other direction. That's also allowed. These are called type Cn. Then one has more interesting ones. that have, at the end of their little caterpillar body, they have 2 antennas. So these are called type Dn. So this is D4 because it has 4 nodes, D5, D6, and so on. This continues. And then there is this one is called E6. This one is called E7. There's E8. There's one that goes by the name F4. And finally, there's one that goes by the name G2, and that involves a triple connection. So this is type A1, A2. This is B2, and that's G2. And to draw the root system for A3, I would need to make a 3-dimensional picture with arrows pointing everywhere in 3 space. And if I wanted to do it for E8, I would need to do the same thing in 8-dimensional space, which I won't do. OK, so this is the starting point. Then we're going to define numbers called di and aij. So I and j label vertices of the Dynkin diagram. So you pick a Dynkin diagram, and now you're going to build a simple Lie algebra starting from this Dynkin diagram. So first I'm going to define some numbers. And, well, let me give you a table. So ij might be equal to each other, might be not connected by an arrow, by a line, might be connected by a line, might be connected by a double line, might be connected by a triple line, or a double line going in the other direction, or a triple line going in the other direction. And then I'll just tell you what aij and what di is in each one of these cases. So di and aij. Okay. Let's see. Oh, actually, I won't give you any information about di in these cases. Here, I will give you the information that di equals dj, but I will not tell you what di is. However, in those cases, I will tell you what it is. It's 2, 3, 1, and 1. And with that information, you can figure out what the di's are for anything. Except, well, when there's a double arrow, then you know what it is. For example, here I know that di is 1 here, and let me write the di for this guy here. So the di is going to be 1 here and 2 there, because that's what these two things say. And then using that rule, I can propagate this 1, and I know that it's like this. When there's no multiple arrows, you might say, well, you don't know what to do. So in that case, let's say that all the di's are equal to 1. So, well, anyways, I just draw it here as an example. Or here also all the di's are equal to 1. Aij are, whoa, this is dangerous. Aij, well, here it is. By the way, this is called the Cartan matrix. And giving the Cartan matrix is equivalent to giving the Dinkin diagram. And, finally, so it's useful to make a distinction between the element of the Lie algebra that lives here, E1, and the element of the Lie algebra that lives there, and the corresponding vectors that live in this two-dimensional space. E1 lives in an 8-dimensional space, namely the Lie algebra SL3. This vector lives in a two-dimensional space. And that vector is called, well, the simple root corresponding to this guy here. So here I would have alpha 1 and alpha 2. These are the simple roots that where the elements E1 and E2 live. And here we have alpha 1 here and alpha 2 there. Here alpha 1, alpha 2. And the other positive roots are positive linear combinations of those simple roots. So alpha I are the simple roots. So suppose you only have this data. How are you going to decide in what geometry to put the alpha i's? Well, that's what I'm going to tell you right now. I'm going to give you an inner product between alpha I and alpha j. There's a formula, actually. It's equal to di aij. And the answer is, well, here you don't know. Here it's 2di. But here it's 0. Here you also don't know. It's minus di. And here it's minus 2, minus 3, minus 2, minus 3. So you start with this Dinkin diagram. You do all this combinatorics. You end up with some values for the inner products. And then suddenly, oh, you know how it sits in n-dimensional space. This n here, is, by the way, is called the rank of the Lie algebra. Okay. So now that we have all that, we can define the Lie algebra corresponding to a Dinkin diagram, and we'll do that by giving some generators and relations. So now I fix a Dinkin diagram. And I will take the following generators. So I have E1, E2, up to En, where n is the rank. F1, F2, up to Fn. And H1, up to Hn. What are the relations? Well, they're given by a list. Hi and Hj commute. Hi Ej is equal to Aij EJ HI Fj is minus A Ij Fj. Then we have EI Fj equals 0 when I different from j. When I equals j, EI Fi is Hi. So for each I, the triple Hi, Ei, Fi forms a copy of SL2. So you can already read this from here. You somehow need to use that. If I put I equals j here, I get Aij, and Aij is the case I equals j of this table, and I read it 2, and that 2 is the same as the 2 that's here. So these are the, and then this one is also part of the SL2 relations. And then finally, we have two slightly more complicated relations. If I take the operator of bracketing with EI, and I apply it Aij plus 1, so now I is different from j. And so Aij is always negative, and that's why I put absolute values, because I really don't like having minus Aij on the board when actually I'm talking about a positive number. So this operator applied this many times to Ej should be equal to 0, and same thing for F. So let's decode a little bit these relations. So, okay, the Hi commutes, that's fine. These two relations here are just saying in these pictures where the EI and the FIs live. So everything inside is graded. I mean, this picture here lives on a lattice. And the HIs, if you know how the HI act, it tells you where you are. I mean, you have the blue HI, the H1, and it tells you how far you are on the left, right. And then the other one tells you how far you are on this side. And if you know both actions, you sort of know where you are on this picture. This lattice is called the weight lattice, by the way. So these two relations are saying what the weight of EI and of EJ and FJ are. And if you work out through all the combinatorics, you will see that the weight of EI is this element alpha I, which is an element of this weight lattice. And the weight of Fi is minus alpha I. They sit opposite to each other. Let's see. So what are these relations here? Well, let's look at what it says in this type A2 case. So in A2, we're in this situation, therefore Aij is 1, and therefore we're asking to repeat this operation twice. Well, what is that operation? It's the operation of acting by E1. So I start with E2, and I act with E1. I'm here, and I act twice. I land out there, and that's 0. So that's what it's saying. You're falling outside of this root system. If you're in type B2, then you're going to have Aij is going to be equal to 2. And, well, you have a little bit more room before you die. You sort of first move once from here to there, and then another time, and it's only the third time that you're going to go to 0. And here you have once more. You have like 1, 2, 3, and it's the fourth time that you land to 0. So this is, so this here, this is 0. It's EI, E1 acting on E2 4 times. Bracket, 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 and then 4 closing brackets. And that should be equal to 0. And that here is what is happening here. Okay, so I have given you a definition of a Lie algebra starting from a Dynkin diagram. And then there is a big theorem that says that these are all the simple Lie algebras. Simple finite dimensional Lie algebras. That's it. Start with these, and then you get everything. You might ask, what happens if I start with something that's not one of these? I mean, say I put an extra leg here to continue and make E9. What would go wrong? And the answer is that if you look at this matrix here that determines the inner product, then that matrix is no longer positive definite. And then you cannot make such a nice picture anymore. I mean, you could make it, but it then no longer lives in Euclidean space. Okay. Here, let me introduce a notation. The weight lattice will be called lambda. Lambda is this thing on which I draw all these dots. Okay, so far I've told you about Lie algebras and their modules in a qualitative way by giving you SL2 and SL3 examples. And I've also given you a definition, a formal definition of all Lie algebras. Now I want to go on and give a formal definition of all representations of these Lie algebras. I don't want to say, look, that's a representation. I want to actually have a definition. So let's see. I will need... I haven't talked about the Borel subalgebra. The Borel subalgebra is the algebra which is generated by the EIs and the HIs. So if you allow me to reuse this picture, so everything that lives here, including the HIs, that's the Borel subalgebra. So EIs and HIs but no FIs. So you have all these positive roots and then all the H's that live here, and that's it. There's also a smaller subalgebra, which is called N, which lives inside B, N for nilpotent, and that's generated just by the EIs, without the HIs. So the stuff that's circled here in blue, well, if you look at the corresponding vectors that live in G, they form a Lie algebra, and that's N. And there's also B minus, which is the opposite thing where you have the Fs, and N minus that has the, well, there's the positive and the negative Borel, the positive and negative nilpotent. Okay, so So we want to construct some modules. More specifically, I want to construct all modules. I will give you the construction, and then I will make a claim that this is the full construction, but I won't actually prove that. So we want to construct finite dimensional representations, but it turns out that maybe for technical reasons, it's easier to first construct some infinite dimensional representations and then use those as an intermediate step towards constructing finite dimensional representations. So these infinite dimensional representations that I'll construct, these are the so-called Verma modules. And they're defined as follows. So you fix an element in the weight lattice. Fix one of those points somewhere. And for this picture, the one that's relevant is the one that's all the way up there. So fix that one. This one is going to be called highest weight. And then do the following construction. So M lambda, the Verma module with highest weight lambda, is by definition the universal enveloping algebra of G tensor over the universal enveloping algebra of the Borel subalgebra with a one-dimensional vector space Okay, so lambda, I said, is a vector in this weight lattice. But if you pick an appropriate basis, then you can write it as an n-tuple of numbers. This is the so-called basis of simple weights. So, okay, so suppose I'm given, well, maybe you don't know what it means, but suppose I'm given just a bunch of numbers, then you know what it means. So I start with this. Hi acts by lambda I, Ei acts by 0, then you can check that this is a representation of the Borel Lie algebra on this one-dimensional space. Okay, so to denote this particular action, we write C sub lambda. As a vector space, it's just C, but this is a representation of B. A Lie algebra representation of B is the same thing as an associative algebra representation of the universal enveloping algebra of B. There's a correspondence between representations of Lie algebras and representations of the universal enveloping algebra. One is in the sense of Lie algebra representations, the other is in the sense of associative algebra representations. So this is a module over UB. And UB sits inside UG, and you just take the tensor product, and you get something, and that's what you call a Verma module. So this is a bit abstract, and I would like to maybe show you what you get in the case of SL2. So before we had a finite collection of dots, and now we have an infinite collection of dots. It continues on the left, not on the right. Here it stops. And then we have the operators E and F from before. Look very similar to what we had before, except for the following twist. So in red, I have the operator E, and in green, I have the operator F. So F keeps going, and E keeps going, except that there's a gap. So this is times 1, times 2, times 3, times 0. I'm not writing it. Times minus 1, times minus 2. And this is times 1, times 2, times 3, times 4, times 5, times 6, times 7, times 8. And then there's, of course, also h, which acts in the same way as before. So h was acting by 1 and by 3, minus 1, minus 3. And then it continues. Minus 5, minus 7, minus 9, minus 11, minus 13. So this is what you get. You get something that contains the piece you care about and then contains some junk that you need to get rid of as on your way towards constructing this finite dimensional module. By the way, this is the picture that you get if you assume that lambda, so this is lambda, if you assume that lambda is positive. If lambda is negative, you can still make the same definition, and what you will get is the same picture except that there's no gap. So you get just something that continues all the way to infinity, and there's no way of extracting a finite dimensional piece from it. But here there's a gap. That's important. So one way of thinking of this Fermat module is to say that it's freely generated by n minus. So by the Fi's. The Fi's act, and there's nothing that tells you when you stop. It never stops. It continues always. And, well, the EI's do what they have to do. Once you know that the Fi's go forever, the EI's are sort of forced on you. So this is the way to think about it. If I call this vector here V lambda, so V lambda is an element of M lambda, and that's the so-called highest weight vector. Then you can say that M lambda is freely generated by the Fi's acting on this particular vector. And this is not really saying anything new. This is just a way to think about what this definition means. So the action of the H's has been prescribed. Hi acts on V lambda this way. The actions of the E's has been prescribed. E acts on V lambda that way. And the other stuff is, well, it does as much as it can. If there's nothing that forces it to be 0, it will not be 0. And here there's nothing that forces it to be 0, so it's not 0. Let me put it in quotes, as this is not something very mathematical precise. So then, if you have m lambda, you can define a quotient of m lambda, of the Verma module, by everything that you want to mod out by. So in this particular picture, you mod out everything that's here, that's a submodule, subrepresentation, and you're left with the thing you want. So L lambda is the quotient of m lambda by I didn't introduce that terminology. The EIs are called raising operators, and the FIs are called lowering operators. So you look at everything that is unable to go back to V lambda by these, you sort of apply these raising operators and expect that eventually you go back to this highest weight vector. Some of the things are unable to do that. For example, in this example, all those are unable to do it because they die here. And then that defines a submodule, subrepresentation, and then you mod out by that. And OK, you get something. It's a non-trivial fact that this will end up being finite dimensional. And actually, it's not always true. It's only true for positive lambda. If I start with a negative lambda, I wouldn't have this gap. And then L lambda wouldn't be any different from M lambda. So let me do an SL3 example. So, well, this is roughly how things go. OK, this here is a schematic for that thing that's over there. That's the finite dimensional representation. And so that's the L lambda. And then we have here on the top the vector V lambda. And if I freely generate on V lambda, I will get something that goes all the way to infinity this way and that way. So all that stuff here that's what M lambda looks like. But then if I go and analyze the situation in detail, what I will see is that along this line I have lowering operators and raising operators. And here there's a gap. And so all that stuff is stuff that's not able to go back by using raising operators. I mean, there's nothing to raise it to. And same thing there. So here also there is a gap. And so what actually you have is there's two submodules that are also isomorphic to Verma modules for a different lambda. That one that starts here so there is a submodule, subrepresentation, which is also a Verma module for this highest weight now. And there's another one here And actually, if you mod out, actually it's enough to mod out by everything that's generated by this and that. And then you've modded out everything that needed to be modded out by, and you have the finite dimensional L lambda. So, more precisely, L lambda is equal to M lambda modulo the span of M sub Si lambda so if this is lambda, so this is the weight lambda, lives here, then this weight here is, let's see, this is the direction of the E2, so that's going to be S2. Acting on lambda is this particular weight, and that's S1 acting on lambda. Okay, so what are these SIs? SI is the operation of reflection across this direction. So I have this line here, and that is S2, and that line here, that is S1. And I want to make a slight notational distinction between the reflection and the shifted reflection. So the reflection would bring this vector to exactly that vector. But that's not the one that's relevant here. The one that's relevant is the one that's one further. So, well, so let me do the following annoying notational convention, which is that if I put a thick bullet, what I mean by definition is the usual reflection minus alpha I. So the usual reflection would bring you here, and then I do one more. And so that's the one that's relevant here, the one that uses this thick, this shifted action of the reflections. Okay, so now there is a theorem that I can state, I won't prove it, which is that any finite dimensional representation of a Lie algebra, of this Lie algebra, is given by this construction, is of the form L lambda, which is a Verma module where lambda is, all these numbers lambda I need to be positive, otherwise you don't find these gaps. So, sorry?
It's a direct sum of those. Those are the simple modules.
Thank you. Yes. So a finite dimensional representation is going to be a priori not irreducible, but it's always going to be a direct sum of irreducible pieces, and the irreducible pieces are those. Thank you. What are the lambdas that are allowed? It's the ones such that applying this operation brings you lower. If I'm on the other side, applying that operation brings me higher up, and then it doesn't. And this isn't even a submodule of that. So you want to restrict to so-called positive weights. A synonym terminology is dominant weight. So you take lambda to be a dominant weight, meaning in lambda plus, and then do that construction. And then there's a theorem that says that you get all finite dimensional modules that way. Okay, my time is up. I think this is actually a good moment to stop.